This video is about the fastest and the most accurate algorithm for runtime 3D edges detection you could possibly have. 0 false negatives, 0 false positives. The video also contains several suggestions for pipelines to prepare your 3D assets for a complex game, because for our technique to work I inherit static body 3D and I also import them with a custom post-import script to bake in some stuff. The video contains history of algorithms refinement process, because author thinks it will make viewers better in Godot. Those who seek immediate knowledge, free from chains of understanding, can find it reiterated in the last minute of the video. I want to start with a message from the bottom of my heart. I think game dev community is living under the influence of self-induced, contagious stupidity. To escape instant labeling of me as a deranged pseudo-critic, I want to quickly remark that my message touches one specific theme of runtime navigation in 3D space. Recently, I lost about 50 hours of my precious life and hobby time on trying to invent a better solution for the classical problem of runtime ledge detection for a game that wants a climbing feature. Starting from a common entry point, I first implemented the two-race solution. Seeing immediately how inaccurate it is, I started to explore different ways to make the system more precise and less vulnerable to unexpected configurations. However, no perfection was in sight and I kept spiraling into trying to invent a magical multi-step configuration of race and shape casts with diminishing returns in accuracy and growing taxes on performance. It didn't help that some direct physics space requests around shape intersections work less than consistently in Godot. For example, what you are looking at as a footage is an edit of what you will get if you ask Godot to return an array of points where sensor shape intersects collision model of some object. And at some point I understood that I ran myself into a corner of designing on the hope principle, using techniques of second-hand awareness based on physical simulation shamanism. Only after some spectacular failures people can break through their delusions. I am not an exception. Stop and think for a second. Can any physical simulation really be considered as a solution to our problem? This two-ray casts method for edge detection is probably an invention of Satan himself, but its worst crime is not being bad, its worst crime is being basic and setting a thinking frame. If this is the first solution you see, it catches you in a trap. It sets you to the path to search for better physical simulation request to solve your geometry problem. But isn't it bullshit from the start? Geometry problems are solved by methods provided by a science called geometry, and physical simulations are physical science domain, so why do we even try to use them? It's like we are trying to teach a blind man to navigate in the space. We can give him more sticks, we can enhance his ears with hearing apparatus, we can train him in safe environment, and we can hope that one day he could develop an ability to echolocate around like a bat. But in reality, our man is not blind, more like he pretends to be disabled for payouts. Maybe the first thing we need to learn how to navigate is to refuse to be blind? Look again at this cube. The engine knows where the edges are. I mean, it literally draws them on the screen each second and does it without any problems. And if the engine can already solve this problem, why can't we use those juicy results to power our game logic as well, am I right? So I went on to LNK documentation surfing session and found out there is a built-in tool class to work with 3D meshes. Mesh Data Tool. Well, my attempt number 0 failed miserably, as this operation that associates a tool with a concrete mesh is very costly. It means that this is not a sort of a singleton static tool, but a per asset tool that you need to prepare in advance, probably already. This led me to inheriting a static body 3D to define my own class called location element. The first serious test for principal usability of this technology was to just intersect each edge of the mesh with the plane. It sort of worked, and even worked at plausible times for the most primitive of cases like these cubes. From there we could just filter the intersected edges to find out ones that intersect not only infinite plane but a finite plane segment, and simultaneously have one of their faces almost vertical and the other one almost horizontal and facing the player. But that approach has some big problems with complex meshes, and to showcase it I installed here a collision shape in the form of Blender's monkey. I want to stress your attention that this is intentionally an overkill task. No one sane in this world must ever use such a shape for their collisions. In a real game this monkey will probably be a sphere plus 3 cuboids, but I use it as a form of stress testing for our technology, because if you showcase an algorithm you'd better showcase it in the worst circumstances, not in ideal. To be real, the first approach didn't work at all. Mesh Data Tool can't be used to solve our problem. The reason is, when you open a 3D mesh for the first time, you would be surprised to know that it has much more faces, edges and vertices than you thought. For faces I knew it, because everything is triangulated, but edges and vertices gave me a big surprise. So for cube with 6 sharp edges, there are 30 edges and 24 vertices. These numbers come from the engine counting each face around the hard edge as a separate thing, so each quad on this cube has 4 vertices, 4 border edges and 1 diagonal edge that triangulates it. And what kills Mesh Data Tool approach is that its edges don't know about the faces they have. Looking at this method, it's logical to assume that an edge laying between 2 faces will return you 2 face indices. However, what happens in reality is this edge returns you 1 face and its copy on the other side returns you the second part. And those edges aren't tied by any data at all. They have different indices, different vertices, etc. The only edges that know 2 faces are diagonal triangulation edges because they don't have a sharp angle. So the first version of the algorithm can get you a bunch of intersections, but it can't analyze a mesh any further. So meet the 1.5 version of the algorithm. Instead of using raw Mesh Data Tool integer arrays, we bake some geometry data on ready. We create a dictionary that will map packed vector 3 array to packed vector 3 array. Yeah. So the first array always holds 2 vectors and they encode an edge in our mesh by 2 vertices. And the second array holds 1 or 2 values, the normals to the faces that are glued by that edge. Normally we expect 2 values for most figures, but there are cases of quads meshes with holes. For example, monkey's eyes in fact are floating parts socketed in. Also our edges are unique because they are used as hash maps keys and can be duplicated. So the 1.5 version is essentially the first version but working. We ask every single edge and filter them by several conditions. Well, life is good, but it can be better. Mesh Data Tool's incompetence was a blessing in disguise, and by moving to our own data pre-processing we destroyed another forced thinking frame. When we were living on Mesh Data Tool arrays, we were thinking in terms of traversing an int array. Surely some operations can be optimized, but any operation that needs to parse the whole array bears the burning brand on its skin. O from N. If you ask every single edge, large amount of edges will drown you. But look at the edges though. Dictionary. I prefer to call this structure hash map, and it is one of the mightiest life hacks humanity had invented. Despite being able to define absolutely bizarre data relations, hash maps save the ability to access their data with speed of O from 1. Now watch my hands. On data preprocessing step we do another map. This map will hold relations of face to its edges. Values will be packed vector 3 arrays, where even indices are starts of edges and odd indices are their ends. And keys will be of type vector 3 and they will represent the normal to the face. If you are a graphical person, imagine that we photograph a mesh and then color only the faces that look exactly at the camera. We then repeat this operation for each face direction present for the mesh. And now, if any tool in the engine will be so kind to return us a normal to a face, we can use that normal as a key to this hash map and get an array containing edges of this face with O from 1 speed. We then traverse this array of edges with O from N, but this time N is actually minuscule because, well, how many edges does a single face direction have, right? So this pre-processing step gave us immunity to amount of edges in the mesh. But we have a long way to go still. All this time we talked about geometry, but we skipped the topic of delivery method, like from where will we get that normal? Originally, the version 2 of the algorithm used a shape cast, a shape of the small strip that I swept horizontally searching for a collision. But this approach had 2 very big problems. First one, collision normal. If the collision occurs on the face of a figure, we get a collision normal of that face, face and we can use it in our request. But if collision occurred on the edge, where most of the collisions occur in real life, we get a collision normal of this edge, and we can't get any of the faces normals from the data. We can cope with a small crutch, we can shape cast, get the collision point, and then raycast like 1 centimeter lower. Raycasting is a discrete operation and you can't get an edge from it, you always get one of the faces. But shapecasts have another big problem. This is the shapecasting variation working on the screen, and when I test it on default cubes, you can tell the difference. However, when I try to run a monkey test for this method, the problem becomes obvious. Even with our geometric calculation costs being immune to complexity of collision shape, our delivery method still suffers from the mesh complexity because, well, it needs to actually solve the collision of two shapes, and to solve a collision with this monkey is not an easy task. So for the final leap, the version 3 of the algorithm ditched the shapecast. Yeah, sort of sucks to return to discrete methods, but as you will soon notice, even casting 20 rays is cheaper than using a shapecast. So what I ended up doing is I made a small helper abstraction, a ray casted zone. In short, we have starting point, direction, depth, height and resolution. With these 5 parameters, I define a rectangle that will fire raycast continuously until it hits something, and the resolution parameter is how little is the distance between two raycasts. For the demonstration on the screen, I use a resolution of 10 cm, which is a huge overkill for any game, but I do it to demonstrate you the system in an optimized condition. And as you see, raycasting is very cheap operation, so with this change we become immune to mesh complexity even on initial physical scan delivery step. Obviously I would want it a complete space sweep, but it's a giant loss of performance, and on the other hand, the complete scan is needed when the detail you hunt is something small, but with our superior search technology we actually need only the normal of the face, so in some sense it doesn't matter where inside that face we shot. Don't need to be a sharpshooter if your arrows are poisoned, am I right? But I didn't finish yet. The search algo is ready, but the technology is awful still. At that moment, we still baked our information on the game's startup. I could cope with it when we talk about cubes, but when the monkey was introduced, my game started to load for 5 seconds. And this, obviously, is a failure. Imagine a town level full of assets. Now you suddenly have a 3 minutes loading screen entering the town, and this is without textures. No, I have some dignity. This baking process obviously needs to be done only once per asset, so it's logical to just write a custom import mechanism for it. But before it, we need to talk about the pipeline in general. As I told earlier, I want an ability to mark things by hands when I want to. For example, this monkey doesn't have any climbable edges per usual rules, but I still want to be able to climb onto its head. Instead of lowering the threshold for definitions of climbable surfaces, I want to introduce an exception for this concrete asset. Moreover, ideally, I don't want to even bring this work into Godot. I would better outsource the job to mark things to some 3D software, as it has much more instruments for it, and the job itself is probably done by someone who provides assets. So we search for a pipeline that will allow us to do some work in Blender and then transfer that information into Godot. But after experimenting with what Mesh Data Tool can offer for such data transfer, I honestly am a bit disappointed. So in my ideal scenario, we don't even go out of the borders of the collision model. For example, here is cube. Imagine it will be some big rock or house. So what I want for customization is to be able to just knife here something like this. And then we mark this concrete edge as a grabbable edge. We mark this as, I don't know, a rope or some rail. And this we can mark as a thin beam to enable that balancing slow walk. Then we do some operation and export the thing as a GLB. This way these edges are in phase. That means that they will be put into static marked data pool, but then they will be deleted during the data triangulation phase and won't have any effect on the collision complexity for this shape. But Mesh Data Tool just can't really do that for us. It has 3 methods to pass some per element information. First is metadata. I poked around for long and I actually couldn't guess at all what is this. It's always null and I didn't make it to export something from Blender to actually use this field. I'm starting to think that this method is planned to use after some work with set metadata counterpart, and this is something that is set here to power solely in Godot meshes changes and not GLB data transfer. The second option is vertex color, but first, I kinda hate Blender's approach to it because it makes your wall mesh into this gradient mix. It really promotes the artistic, non-discrete way of setting things up with brushes, etc. But we want to pass some discrete data, so what you will end up doing is you will select some vertices in edit mode, then change mode to vertex paint, then select vertex selection mode inside vertex paint, and then manually set the color of these vertices. And the worst news are actually not that. The worst news is that GLB format doesn't transfer vertices colors out of the box. I kid you not, this bullshit doesn't work, they straight up disappear. So you either need to invent some actual material to use your vertex color as input for Blender to agree to export them, or you need to install some special Godot add-on for fixing that problem and then export vertex color as a separate meta attribute, and then only to touch it in Godot. I am good, thanks. You can escape this by exporting as FBX, but FBX format has a bunch of other problems that I won't even go into. If you are interested, you can ask in comments or in Discord. The second option is to use bones. Bones actually can be bound to vertices with vertex groups, and this workflow actually looks much more likable than the vertex coloring. Just add whatever skeleton, name its bones as your edge mark groups, and then you can just select vertices in edit mode and put them in a group. But this workflow has a big arrow in its knee. Godot and actually most of game engines allow only 4 bone influences per vertex. It means that in your marking system you are limited to 4 tags per imported asset. Kinda as if you ask me. I only try to invent this pipeline and it already tries to impose limitations on me. We can try to invent something with UV usages for our marks, but this starts to look more and more like competitive self-hatred. So what I ended up doing is I put aside the idea of using the same mesh to transfer data altogether. Instead, just export these edges like a different mesh and solve their names with some postfixes that will power post-import script for me. For example, let's mark the monkey with a climbable edge. I can enable surface snapping and quickly draw something like this. Now I name this additional mesh in a way my conversion map tells me, so ledge. You also need to check these checkboxes when exporting. Without them, Godot won't consider our edges as a mesh and will ignore it. And finally, when importing, I also do some work setup in the node. First I search for the data mesh by the call mesh hint word in mesh's name, I then add collision shape sample from that mesh and I bake my data into object fields. Then I search for static marked objects. Here I have a map for input hints. Currently there is only one ledge that is present, but we will get more. If I find any, I bake their data too and delete the node from the scene. As always, Godot tried to throw some sticks in the wheel. Turns out mesh data tool just refuses to work if there are no faces in your mesh, and we specifically use only edges because we want to transfer a line. So we use data from one level lower by requesting absolutely raw list of points from the mesh. They aren't so usable usually, but we can work with them because we specifically encode a single line of edges. Also, there is a strange hiccup. When I try to set up internal fields values for the class, I get nulls if the fields aren't exported, but I get them set if they are. If anyone knows why, please tell me. Of course, I don't think we need to export all the data, but without this step, everything is zeroed. So this import script basically allows me to do that baking operation outside of runtime. My game slows and times don't expand, and what's even more important, I don't need to set up anything by hands in editor. I can just drag and drop GLBs around. And now during the runtime I can scan this monkeys model and I will find those edges. They don't exist as any mesh. They exist purely as vector 3 data in this monkey's imagination, but they can be sensed and returned, because when I request climbable edges, I first look through any static marked ledges and then only through the baked geometry. That's it. Also recently I qualified for YouTube partnership, but the channel probably will stay forever adless, so as always huge thanks to my wonderful Patreon supporters. This video and all other ones are dedicated to them. Finally, a repetition for people who feel lost and for people who ignored the journey. We inherit static body 3D and use a custom import script to import location assets. In the script, we bake a lot of geometry data into these assets fields. First, we bake edges data in the form of hash map, where keys are edges encoded as its two vertices in array, and values are normals of faces those edges glue together. Then we bake another hash map for faces. Its keys are vector 3s that store faces normal, and its values are the edges of all faces with such a normal. Even indices are edges starts and odd indices are edges ends. Then in runtime we cast a ray in any direction, and if it hits a face of this object collision mesh, we take the collision normal, we use it as a key in faces hash map to get the list of edges that this face can possibly have with O from 1 speed. We then quickly traverse that short list of edges asking for edges hash map if they intersect our sensor plane segment, and if they are, we look at their normals and see if this edge implements the pattern when one normal is almost vertical and the other normal is almost horizontal. If they do, we return an array of 3 vectors: edges start, edges end, and the sensor plane intersection point, because we most probably use it for climbing algorithms. You can ask what climbing algorithms one can implement with complete understanding of location around on the geometry level. Well, I would ask, what can't I? Tune in for the next episodes to find out.